Hello, everybody. My name is Lou Ternullo, and I'm part of the Interface IP team at Rambus. And today I'm going to talk to you about system-level trends and design considerations for PCIe 6 and future generations of PCI Express. The future of PCI Express system design. PCI Express, also referred to as PCIe, is today's de facto interconnect between CPUs and peripherals. All server-based CPUs, whether x86 or ARM or whatever, use PCI Express to connect to peripherals. And I'll talk more about what types of peripherals that are most common and where the challenges are. Doubling speeds every generation, going from Gen 5 to Gen 6 and the future Gen 7. Maintaining the same form factor, motherboards sizes aren't getting any smaller, so the same reach, compound challenges in system design. There's also a drive from the industry to reduce costs, and one way to do this is by disaggregating some of the components that are attached to the server systems. And I'll talk to you about some of the challenges and or considerations in implementing this disaggregation methodology as customers start developing their systems moving forward. Before I jump into the meat of the presentation, I want to level set the audience here with some definitions and metrics that I'm going to use throughout the presentation. So I've already talked about disaggregation. So what is disaggregation? Fundamentally, it's dividing components and resources into subsystems. So historically, you'll have a CPU and you'll have everything connected directly to that CPU, i.e. memory, storage, accelerator cards, and what have you. Disaggregation allows for a distribution or division of the components across different parts of the system so that you're not all piled into one server, one rack, and so forth. Fabric attached is another terminology that you may have heard a lot about in the industry, and I'll talk a little bit about it in this presentation and how it relates to some of the design challenges. And essentially, the term fabric is, if you can visualize fabric, it's like a mesh of in a cloth, and it essentially works the same way in this a server system, networks, and so forth. It allows accessibility across a series of servers and components in almost any direction, point to point. GFAM, which is the acronym for Global Fabric Attached Memory. Again, that's memory that's attached in this fabric, so servers across the network or across a fabric mesh can access it. Stranded memory is also another term I'm going to refer to, which is one of the motivations that's driving disaggregation. And stranded memory is defined as memory that's attached to a CPU that is accessed infrequently or not at all for those types of applications and workloads that are being run in those systems. And real briefly, you might ask, well, why would someone design a system like that? And the challenge is when a hyperscaler or a company is putting together a server system, they populate it with storage and memory and so forth to support a variety of different workloads. But the average case is what's looked at. And more often than not, if you do a search on stranded memory and start reading articles, what you'll see is that 40 to up to 40 to 50% of a DRAM that's directly attached to a server may not be accessed the majority of the time. And the total cost of memory in a server system can be anywhere from 30 to 50% of the total cost of the server. And so if you do some rough math and assume 50% cost, you assume a 50% DRAM utilization, so in other words, only half of it. And so if you're doing attached type storage or memories that are referred to pooling, and by doing pooling, computationally you can reduce the DRAM by about 10%, that means your total savings could be anywhere from 4 to 5%. So it's not insignificant. So moving to the next slide here, I just want to introduce the audience to typical applications that are using PCI Express and CXL today. Before I jump into these, I also want to mention PCIe is an interface, and it's used very prolifically in the semiconductor industry. It's also used in die-to-die for low pin count, high-speed interfaces. Some of you may be familiar with mobile phones that have an application processor and a radio, and in a number of cases, the application processor is connected to the radio, which are two separate die, via PCI Express. So it's an interface standard. Because it is a standard, it's used almost ubiquitously. Today, I'm going to focus on servers and databases and so forth, and I'm going to focus on these types of applications that you see here. So starting in the upper left corner, high performance compute, cloud, edge computing, all using server CPUs. And the way the server connects to peripherals is through PCI Express. And some of the peripherals in particular include enterprise storage, SSDs, as you can see here in the center, upper center, more and more SSDs. And as the applications get more and more complicated, more and more data is required, density, performance, moving from Gen 5 to Gen 6, and in the future Gen 7, enterprise storage is a key aspect, and a fairly reasonable high bill of material count in server CPUs. On the order of 15% of the total server goes to storage. Enterprise and networking. Historically, these have been referred to as NIC or network interconnect cards. Nowadays, you'll hear more of what's called a smart NIC, which typically embeds like a data processing unit or a DPU. The point of doing a smart NIC is to offload the management of the network to a different compute engine and not relying on the server CPU to, in addition to the computations that your software application wants to run, to also manage all this network type traffic. And so that's the purpose of a smart NIC, and that market is growing quite dramatically in the order of 25% compounded annual growth rate through roughly the year 2030. In the lower left, now we come to something that everybody's probably heard about in the industry is artificial intelligence, machine learning, and inference. And so more and more connectivity to the server CPUs are with either graphic accelerator cards or FPGA-based or even ASIC-based AI engines, as you've heard in the industry. Google has the TPU, Amazon has Trainium, you've heard of Habana from Intel, and so forth. So these are all attached to the server via PCI Express. And a little quick note about AI and the importance of, PCIe and the growing importance of the connectivity is the growth of artificial intelligence. Hardware artificial intelligence products are growing on the rate of approximately 25% compounded annual growth rate. And so again, the importance of PCI Express and connectivity to the server CPU will continue to grow with that. Test and measurement, suffice to say, it does require and use PCI Express. I'm not going to talk too much about this in the upcoming applications that I'm going to discuss. Automotive, again, not in particular, but I will tie some things to the automotive application. A lot of automotive automatic driver assist is, in some sense, AI-based. Communication with 5G towers, moving to 6G, from a mobile network perspective, is going to interconnect the cars as they commute and travel on the road. And so all of those types of products leverage PCI Express. Real quickly, I'm not going to spend too much time on this, but I want to talk about the transitions from generations. Today, we're talking about PCI Express 6, which you see it, the second row from the bottom, 64 gigabit transfers, and the release year was and date was roughly January 2022. Gen 7, PCI Express Gen 7 is going to double from 64 gigatransfers per lane to 128. And the anticipated date of the spec releases is the late 2025. Talking briefly about PCIe 6 goals and what implications those goals are having on the system. So as we mentioned, doubling the bandwidth between generations, so going from Gen 5 to Gen 6, going from 32 gigatransfers to 64 gigatransfers. And then there's the mandatory backward compatibility to Gen 1 for link up. Similar channel reach versus PCIe 5. I am going to talk quite a bit about this and the implications of it and higher bandwidth efficiency. So what does this have? What implications do these changes, if you will, in moving to PCIe 6 have on the system design? Well, it's going to increase the board design complexity, and it's going to increase the cost. Having that same reach, the same travel distance, if you will, on the board, adding cards and so forth, and doubling that data rate and moving from an NRZ to a PAM4 is going to have an implication on the types of materials, design complexity, potentially layer count on the boards, and adding cards. So that adds cost, that adds complexity. The longer reach for riser cards and backplanes. I'm going to talk a little bit about this as well. So there are a number of cases that require more than one adding card to be connected to a server CPU, which has a minimal number of slots. And so therefore you have riser cards, you have backplanes. And so that increases the reach. And as I mentioned, it's disaggregation. So there is this market demand for further disaggregation, which means separation of these components, which means further expansion and distance between the server and the point that it's trying to reach. Real briefly, I want to show you this slide here in particular to show you the actual physical aspects of the data eye itself. The image on the left is Gen 5, which is NRZ. So you can see that eye diagram, pretty wide, pretty open. Moves to the Gen 6, moves to PAM4. Gen 7 will be PAM4 as well. Pulse amplitude modulation is what PAM stands for. And you can see that you're if you want to call it noise or what have you, but because you're dividing that same amplitude in 3 eyes, you're reducing the amplitude for sure, but you're also reducing the UI, the unit interval in which you can the receivers can sample the eye. So it adds a lot of complexity. There are features that are added, like the FAC in Gen 6, which helps improve bit error rate. The addition of the FLIT interface, low power mode. The L0P is a new power mode interface that's added to Gen 6 as well as the pipe interface. So all these are new additions. A lot of them are in part because that you're reducing bit error rate and need to improve the signal quality. Now I'm going to jump a little bit more into the meat of the presentation, system level considerations and challenges. So this is comparing Gen 5 to Gen 6, where we're using Gen 5 as a reference. Signal to noise reduction, roughly moving to a PAM4 signal, we're losing approximately 9 dB of signal. From a unit interval timing loss perspective, roughly a third, if you recall the eye diagram I showed you on the previous slide, roughly a third of that window is being reduced because of PAM4. Now the pad-to-pad loss budget. So these two reaches, if you will, the 36 dB for Gen 5 and 32 dB for Gen 6, these are what the spec calls for. And if the systems are designed to that spec, what you see below, root complex, adding card and system, this is the estimated amount of loss for each of the components to ultimately add up to 36 for Gen 5 or 32 for Gen 6. And this is all at the Nyquist frequency of 16 gigahertz. In addition to all of that, you can see the diagram below. This is essentially what you'll see if you open up the specification from the SIG. You'll notice there's a root complex or CPU on a PCB, and it calls for 12 to 14 inches of trace. So a system with these dimensions should theoretically be able to work by plugging it in and interoperating. So you have an adding card, which adds 3 to 4 inches, and from that pin to the root complex or the CPU, roughly 12 to 14 inches. So in total, 18 inches, roughly, kind of a max length. And so that's what these systems are typically intended to support, because as I mentioned before, the motherboard sizes are not decreasing. And so moving from Gen 5 to Gen 6, designing these boards with the same reach is going to have implications, as I mentioned, potentially improved dielectric material, tighter manufacturing tolerances, higher layer count, et cetera, and all adds cost. So I want to talk about how do we extend that reach, and so what I'm showing here is talk a little bit about retimers. And what a retimer is, it captures and generates a new source signal. You may have also heard of something called a redriver. A redriver is essentially an amplifier. And so it takes the signal coming in and it amplifies it and sends it out. The problem with a redriver is it amplifies the signal, but it amplifies the noise as well. And so a retimer has the SerDes on both ends, obviously receive in, transmit out, but it has, the retimer controller in between, which, enables the protocol to be remapped, if you will, and send downstream. Over on the right side, the top two diagrams I'll show you are examples of what I mentioned in previous slides, the riser card and the backplane. So the top one is a riser card. And so what this is showing is a motherboard with the approximate dimensions I talked about in the previous slide. And then there's a card vertically here, and then the adding card goes into it. And so that reach is going to be longer than the roughly 16 to 18 inches of trace that we talked about vis-a-vis the spec. And so you'll see that the orange little chip on the riser card, that's called a retimer. And so that's one application for a retimer, where you're actually extending the reach using a riser card. Below that, you have a backplane. And so this is just showing 2 slots, but a backplane could have multiple slots and tied to other things, and 2 processors can be communicating with each other. And therefore, in this particular example, is showing the retimer on the motherboard. Now, in the case of the riser card, the retimer could be on the motherboard, it could be on the riser card, and so forth. These are just showing you examples of where these retimers could be in these types of scenarios where you're extending the reach beyond what the spec calls for. The other use model for retimers is to make total system cost trade-offs. So ultimately, the whole system costs there's some value, some price associated with it, and the components of that price vary, but moving to a higher data rate like in Gen 6, as I mentioned, more costly PCB materials, more costly manufacturing process, and what you can use a retimer for, obviously, is if you wanted to use more cost-effective materials and reduce the physical reach, but put a retimer chip in there. And so now you're doing a total bill of materials cost, where potentially you could reduce the manufacturing cost of your board and your adding card to a certain degree that you can actually purchase a retimer chip, put it in there, and the total cost would be less, hypothetically speaking. The other aspect is that when SerDes are talking to each other, a root complex to an adding card from one vendor, or an adding card from another vendor, they operate differently. The reach may or may not work. Maybe it supports the 32 dB, maybe it's a little less. A retimer adds a little more confidence, a little bit. It kind of gives you a little bit more possibilities from permutations and combinations of manufacturing tolerances. So it adds a reduced risk value as well. And so there is some value associated with that. So these are all different aspects associated with the potential of using retimer designs as these PCIe Express data rates get faster and faster, and these designs get more and more complicated. Negative impacts are increased cost, increased latency, and you can only, per the spec, piggyback to retimer. So this all needs to be managed in system design that customers are putting together with their products. Switches. Now I want to talk to you about a little bit about switches. And so we talked about disaggregation, and retimer gives you longer reach. Switches will give you more access to more compute, more storage, and so forth. And so below, starting in the lower left, you see a CPU with a couple of components attached to it, a couple SSDs, a network interconnect card, and GPU. As we shift over to the next image on the right, JBOF stands for just a bunch of flash. So you see a CPU talking to a cascading switch network, PCIe switch network, to a bunch of SSDs. It could be cascading, could be one switch to a bunch of SSDs, and so forth. To the right of that, show you an example with, again, a CPU communicating with the switch with GPUs or potentially accelerators. And last but not least, on the far right, I threw this in here to show you the direction the industry is more than likely going toward is fabric attached, and this is using CXL right now. And I tried to keep the colors consistent, and so the purple is CPU, and the dark green is GPU. And below the switch, you can see there's two CPUs attached to a CXL switch. There's memory attached to it, potentially memory expansion, and there's a GPU attached to it. And in the center switch column, you see that global fabric attached memory, and on the far right, you see the network interconnect card. And as I mentioned, in the fabric attached, any one of these components can talk to the other. So CPU can talk to every single one of those components, whether it's connected to the same TXL switch or the one on the far right through the fabric. And conversely, there's features called peer-to-peer, where NIC cards can talk to each other for various purposes. The memory can talk to the NIC card or what have you. Now I want to introduce you to a little bit of what Rambus offers from an IP perspective. So this slide here, it references PCIe 6, but in general, PCI Express controllers, very flexible, native synchronous interface, or AMBA, an AXI, supports the FLIT, non-FLIT mode in the context of Gen 6 requires FLITs, Gen 5 doesn't. Optional IDE security engine, more and more discussion with data encryption. So IDE stands for integrity and data encryption. And a couple other things I do want to mention is that RTL for these controllers are able to be generated to be supported in FPGA or in ASIC. So if you need to do or would prefer to do a prototype in an FPGA and then take it to ASIC, the RTL, which is generated from our configurator GUI, will allow you to do that with the same register map. A brief note on the PHY. So on the physical layer side, moving to PAM4 leverages the DSP architecture, FFE and DFE equalizers, built-in self-test, real-time receive data I monitoring, and SHMU for debug and diagnostics, and per-channel PRBS, user-defined pattern generation. From another IP we offer is retimer IP. And so, quick note, the diagram on the right is the actual retimer chip. And what I show here is the light-colored orange boxes are SerDes. And so it could be a customer developing a retimer chip that has their own SerDes, or they could license a Rambus SerDes. The light blue boxes are the IP that are provided by Rambus with respect to the retimer IP. So that's the controller and the debug analyzer, which gives customers the flexibility to go in, to inject errors, to monitor, to reset registers, and so forth. So it's a very powerful tool to help customers debug and or bring up their system. Couple things about the retimer IP: CXL aware, allowing the CXL synchronous header bypass supported by the SerDes, optimizing the data path for low latency insertion, very highly configurable equalization algorithms, and the IP itself supports the L0P power saving mode in PCIe 6. Rambus also offers switch IP, diagram on the right showing a single upstream port to multiple downstream ports, up to 31 ports, supporting the various data rates for PCI Express up to Gen 5, advanced error reporting, end-to-end CRC, lane reversal, a number of features that are supported in the switch. It even supports peer-to-peer transactions between downstream ports. And peer-to-peer essentially means from port to port without having to go back to the host. This also is supported, the RTL code base is supported for ASIC or FPGAs. Key takeaways: advances in PCI Express are bringing system-level design challenges that, as an industry, we have to contend with. Higher data rates are driving improved channels, improved materials, higher tolerance manufacturing processes. Demand for longer reach and or increase in material costs leads to the use of retimers, and disaggregation leads to the increased use of switches. So we're seeing more and more demand in the market for PCIe retimers and switches, and not to mention fabric attached, which is driving CXL type switches in the chip business. Rambus PCIe IP benefits over 20 years of experience in PCIe controllers, architecture and development, and a very long history of SerDes, signal integrity and power integrity, and the pioneering of PAM4 experience for our customers. With that, I'd like to thank you for attending this presentation. Please go to rambus.com if you have any other questions and want to learn more about our products.